Okay, so welcome, and now we're going to investigate the question, does continuity imply differentiability? Now in the last video, or the video before, I can't remember which, but I said that the implication only goes one way. That if a function is differentiable at a point, then it must be continuous at that point. And it doesn't go the other way. But let's investigate whether that indeed is true or not. So let's take the function here. Here's an example of a function that is continuous everywhere. It's the absolute value function. So it's continuous everywhere on the number line. Okay, so here we go. We got our x-axis, our y-axis. Okay, and so we want to investigate if it's differentiable at 0, right? So now here's the thing. The derivative at 0, so f prime of 0 is undefined. So this observation leads us to believe that it isn't differentiable. That differentiability does not imply continuity. Or excuse me, continuity does not imply differentiability. Okay? But let's explore it. Okay? So let's do the limit as x approaches 0. Okay, so we can see something's going on at 0. Okay? It's obviously continuous looking at the graph, right? But let's see what we get. Okay, so this is going to be f prime of 0 equals the limit as x approaches 0 of f of x minus f of 0 over x minus 0. And so this is going to be the absolute value of x minus the absolute value of 0 over x, which gives us obviously the absolute value of x over x, which we've looked at before. Okay? Now, we know this function is undefined at 0. And in fact, the limit does not exist at 0 for this function because the limit as x approaches 0 from the left of the absolute value of x over x is going to be -1, and the limit as x approaches 0 from the right of absolute value of x over x is +1. And therefore the limit does not exist, and therefore is not differentiable at 0. Okay, so there's an example of a function that is continuous at 0, but not differentiable. Okay, so let's consider some other situations. Let's look at another function. Okay, so this function is going to be the cube root of 3. So let's f of x equals, or excuse me, the cube root of x. I said the cube root of 3, but it's the cube root of x. And so what does this function look like? Well, this function looks like this. Okay, and I'll grab my, so it looks something like this. Right? So this is f of x equals the cube root of 3. You should know this. Oops, not cube root of 3, cube root of x. Okay, this is one of the basic toolbox functions you should have learned many classes ago in either pre-calculus or algebra. So, but this is one of the college college algebra, especially in college algebra, any algebra class, you probably should have seen this one. So this is the cube root function, okay? Okay, so now we see something's going on at 0, okay? So obviously, again, this is something that's continuous everywhere. It's obviously continuous along the whole domain, along the all real numbers. So, but let's investigate what's going on at 0, because it looks like the tangent line at 0 is vertical, which means the slope is undefined. So let's investigate. So now what we're going to do is we're going to, again, this is continuous everywhere, but now we're going to test at 0. So we want f prime of 0 equals the limit as x approaches 0 of f of x minus f of 0 over x minus 0 again, which again is going to give us the cube root of 3, or excuse me, keep saying cube root of 3, cube root of x minus the cube root of 0 over x, and so now in this case we get, oh, I dropped the limit again. The limit as x approaches 0 of cube root of x minus the cube root of 0 over x, which is going to give me the limit as x approaches 0 of, well, here's what we get. We get the cube root of x over x. Which is going to give me what? Well, this is going to give me 1 over x to the 2/3. Right? Oh, the limit again. Keep forgetting to put the limit. So this is the limit as x approaches 0. So it's going to give me 1 over x to the 2/3, which is going to be the cube root of x squared, right? Same thing. So either 1 over x to the 2/3 power or 1 over the cube root of x squared. Okay? And obviously, as x gets closer and closer to 0, this thing is going to infinity. But again, if we look at to the left of 0, and the right of 0, it's both going to positive infinity. Okay? Because whether it's coming from the left, the negative side, or the positive side, you're squaring it, so you're going to end up getting a positive number that's going closer and closer to 0 at the bottom, where this is 1, so it's getting bigger and bigger positive. Okay, and so therefore the limit doesn't exist, and it's not differentiable. Okay, one more. Let's look at a piecewise function. So in this example, we have f of x equal to x sine x, or excuse me, I'm sorry, that's x sine x, 1 over x. And then that's for x not equal to 0, and then for x equal to 0, it'll be just 0. Okay, so that's a piecewise function. So this is another function that's continuous everywhere because it's defined at 0 and everywhere else. Okay, so it is continuous. Okay, but is it differentiable at 0? Because there's definitely something going on at 0. If you look at the graph here, just because I'm not going to draw it, here's what the graph looks like. Definitely something interesting is going on at 0. Okay, so let's investigate what we see. Okay, so f prime of 0 equals the limit as x approaches 0. And we're going to have, again, f of x minus f of 0 over x minus 0, which gives us, and again, we're not at 0. So this is okay, we're not at 0. So this is going to be x sine 1 over x minus 0 times sine of 1 over 0 over x right? Because, oh, no. No, that's not right. I forgot. It's piecewise function here. So at 0, it's 0. So this is just going to be 0. So, so what do we get? We end up getting the limit, oh gosh darn it, I keep dropping limits. Dropping limits all over the place. Okay, equals limit as x approaches 0 of, let's do this again. So it'll be x sine of 1 over x minus 0 over x, right? And so guess what? This is 0. So that goes away, and now the x's cancel, and we get the limit as x approaches 0 of sine of 1 over x. Well, this doesn't exist. Okay? So the slope of this thing is constantly changing direction as it goes, x goes to infinity. So this definitely does not exist. Because as you can see, sine just goes back and forth between -1 and 1, right? It oscillates back and forth. What's happening to this thing? Well, this angle inside is just going off to infinity. In fact, if you approach it from the left, this is going to negative infinity. And if you approach it from the right, this angle is going to positive infinity. So it's just basically just keeps oscillating back and forth. Okay? And so it's never going towards an individual point or an individual L value, real number. So therefore it doesn't exist. Okay, so therefore it's continuous, another continuous function that is not differentiable at a point. Okay, that's it. Next time we'll go over the summary, and then we'll wrap up things for this section. Or not this section, but this topic. Have a good day.